Okay, we've got a little bit of stuff to get through today, so let's go ahead and get started here. Today we're going to be talking about TCPIP, and we talked about the OSI model last time. TCPIP is kind of the protocol that runs the internet, so we're going to talk about how it relates to the OSI model a little bit. But let's go and get started on what we want to cover today. So first off, looking at that OSI model's layered approach. Again, the idea of that was creating these protocols that can work across a variety of different network systems and for a whole range of different applications. So the idea there is you want to be able to have your DSL connection talk to a server that's on a fiber optic link somewhere. You want to have your Ethernet plugged in server talk to laptops that have some sort of Wi-Fi capability, or maybe even internet access to the internet. And in order to do that with these different kinds of networks, we need to have some kind of layered approach to that, so we can take off the outside packet of the physical part, rewrap it in another thing, and not have to kind of tear the whole thing apart. So in other words, that layered approach is really important to do that. Now, for something like the internet to exist, we need to have that ability. We need to have something that has the ability to have completely different kinds of networks connected to each other. And TCP/IP was the technology that emerged that allowed that to happen. And it's really kind of the foundational protocol for the internet. So the protocol suite, I should say, because TCP and IP has multiple layers in that OSI model that are implemented. Okay, so what is TCP/IP? Let's go through this list of bullets quickly. So it's a layered set of protocols for network communication. And the idea there behind it being layered, just like in the OSI model, is that each layer provides some set of functions. You can think of it like a library of routines or a library of capabilities. And it was designed to work on the internet, but can also be used on LANs as well. In other words, you could use it on a local area network or to connect the entire world together. It was created in the 70s by the DARPA kind of Defense Advanced Research Projects Agency as a way to link together a whole lot of different research computing centers and academic centers. They wanted a way to connect all of those kind of previously separate networks together. So they created kind of a group that came up with what is now the internet. And that was created as a connectionless paradigm. And what that means is that it's not like a telephone. On a telephone system, you pick up the phone, you dial a number, you're connected to the person on the other end. You have a conversation. You actually, in the old way the telephone system would work, you would talk on the phone. Your line would physically be connected to the phone system, which would physically connect to some other phone system, which would physically connect to something, which would eventually connect to the other end. So when you were talking on the phone, you had a connection all the way through from your telephone to the person you were talking to's telephone. TCP/IP isn't like that. It's connectionless, which means that it's built on a packet switched network type. So in other words, you're just dropping these little packets onto the network. They're traveling through to the other end. And that is what that next thing says. Information is transferred as a sequence of what we'd call datagrams. And you can think of a datagram like a message in an envelope. So you have this message stored inside of a envelope. Like here's a piece of paper. Here's some data that I want to send. I put this in an envelope, and then I drop that in the postal system. And it finds its way to the receiving end by routing that envelope around. So think about a datagram like an envelope with data in it. And that's what we say on the next thing. A datagram is a collection of data that's sent as a single message. And the outside of that envelope or around that envelope, we're going to have some routing information, some other stuff to get it to an end. But each datagram is sent through the network individually. In other words, if I have a large message that's too big for one envelope, one datagram, I have to divide it up into multiple ones, throw them all into the network. They'll all make their way to the other end, but that does have some problems. Sometimes letters could get lost or datagrams could get lost. Other times the order you drop them in might be different than the order they end up on the other end. So again, think of a packet switch network a lot like the postal system with individual letters. All right, now what are the layers of TCP/IP? The main layers that or a way to think of this is kind of the application layer, and that's something that's using TCP/IP to do something. That's not really a layer specifically of TCP/IP, but it's a layer of kind of communication here. So the application might be a web browser, and it wants to connect to some web page or a web server somewhere else and download the web page and render it. And so the idea here is that application layer would be the application that's using the network for something. The next layer down from that is the transport layer. That's where TCP sits. So TCP sits in this transport layer, and that transport layer, what TCP is doing is providing services for the reliable transfer of those datagrams. In other words, making sure that if one gets lost, it gets re-requested. And then also having it so you can create a session. You can open a connection, you can send data through, you can close the connection when you're done. But behind the scenes, it's not really a connection. It's just a bunch of datagrams going through. So there needs to be some kind of special way of saying, I'm starting this session. Okay, you're allowed to talk. They communicate, datagrams go back and forth. So it looks to the user of the application just like a stream of data. But behind the scenes, it's a bunch of these datagrams going back and forth. The other thing that TCP does is it divides up the large stream of data or a large block of data to these smaller datagrams. It'll make sure it puts them back together in the right order. But one thing to notice that TCP doesn't do is there's nothing in here about addressing. It has a TCP part of this, the transport part of this has nothing to do with the addresses, only with making sure the packets get through reliably and in the same order that they were sent. And that we can start a session and end a session. Now, one thing to note is that this transport layer, the TCP part of TCP/IP, kind of crosses multiple layers of the OSI model. We've got kind of the session level, the transport or session layer, transport layer, and then maybe even a little bit of the presentation layer, all kind of wrapped into this one discrete block here called TCP. Now below that is the IP. That is what adds the addresses to the packets. That's the basic service of getting them into the network and out of the network. And so IP is where addressing comes into play. TCP does not have addressing associated with it. IP does. So in other words, we took this type of datagram, made a new type of datagram that now has addressing associated with it, and then we now have to put that on a physical network. So the addressing that's on an IP part of it is kind of a logical address, we'll talk about those a little more in a second. But the network part of this is actually putting the packet onto some physical wire or Wi-Fi or whatever the physical network medium or interface is. So the network interface layer is what takes the IP packets, wraps them in yet another kind of datagram, and then drops them on the actual network. So applications use TCP. TCP uses IP. IP uses the network interface to send data out on the network. And when it gets received on the other end, the receiving network interface is going to receive it. Excuse me. Good thing you were remote. The IP end receives that and then passes it up to TCP, which then passes it up to the application. So in other words, you can see that kind of layered approach at work here where data comes from the application, goes through TCP, IP onto the network, travels all the way across the internet, and then gets pulled off of that network. And some things happen in the middle there. We'll talk about that in a little bit. But then it goes back up through those layers back to the application on the receiving end. Okay, the TCP/IP application layer. Really, that's outside the scope of TCP/IP, like we said, but it'll make calls to TCP/IP functions to configure the network, to open a connection, to listen for incoming connections, things like that. So notice that our program is going to interact with the TCP/IP subsystem through a set of function calls. The layer, the application layer, is kind of the application presentation layers in the OSI model. The idea behind that is that we're just dealing with the data using TCP/IP as its resource. The application could be a game, web browser, file transfer, anything that uses the internet, basically. It could be a industrial machine that sits on the internet that you can control over the network in some way or report statistics in some way. It could be your internet-connected coffee machine or something like that. All right, the TCP layer. TCP stands for Transmission Control Protocol. And remember, it's responsible for making sure the data gets through to the other end reliably. In other words, if TCP says this was sent, you are guaranteed that it was received on the other end. It also keeps track of sequencing the datagram. So if I say, hey, send this really large file, TCP will handle dividing that up into smaller datagrams and then putting them back together on the other end in the right order. And if any parts are missing, it'll handle seamlessly and silently getting the parts that were missing and putting them, re-requesting them, plugging them back in. So if datagrams fail, it will automatically retransmit any missing or damaged data. So it is handling that for us. We don't, in the application layer, have to worry about any of that. We can just say open a TCP connection, push data through. If it says success, we know it got to the other end, which is pretty cool considering that behind the scenes it's relying on this kind of unreliable datagram system. All right, so again, any message that's too large for one datagram, it'll split it up in several. It'll add sequencing information to them, make sure they all arrive correctly and in the right order. And then in order to do its job, it adds a header around your data or onto your data. So in other words, if you have your data, TCP adds this kind of header on the front of that. Now the IP layer is the next layer down. And we said what that does, it takes those TCP datagrams and adds addressing and routing information. So it adds another header onto that. And what's IP's job? It's to find a route to get the packet to the destination. So in other words, IP, we put the addressing information on there, drop it into the network. Some router somewhere will look at the address that's in it and say, hey, this isn't in my network. I'll pass it upwards. And eventually it'll get to a place where, oh, I know where that is. That means you're trying to talk to google.com or microsoft.com or whatever you're trying to talk to. And it has the address of that, passes it to the right router that eventually the packet will get there. A lot like the postal mail system. So one thing to note that IP addresses are logical addresses. In other words, they're configured in software on the machine. So if you have a server, you'll have what is called like a static IP assigned to it. Like you think of an IP like a assignable telephone number that you basically say, okay, this IP is associated with this machine. But it's not a physical hardware address. It's something that is being assigned to that machine. Okay, network interface layer. We're going to talk specifically today about Ethernet. And Ethernet, to kind of quickly give an overview of that, there are a lot of other choices, but Ethernet is, and some variant of it is kind of one of the more popular ones, whether it's wireless Ethernet, Wi-Fi, or whether it's a wired Ethernet. But it's designed as a broadcast medium, meaning that it'll send out a message to every station on a hub. But if you use a switch, the switches are kind of smart and they will filter it by this message came or is going to this particular thing, don't send it to everybody. So switches kind of cut down on that being broadcast. But the original design of Ethernet, every node on some segment would get every message that was put onto the network. Now, each card has its own unique MAC address, and those are actually hardware addresses, which we'll talk about in a second. But essentially, we want to convert each IP datagram into an actual packet that goes across the network. And again, we have this TCP packet. We add a header onto that. We add a header onto that for the IP part of it. And then we add the Ethernet header on top of that. So we end up with this packet that has all of those parts added onto the front of it. And notice that the Ethernet has its own header that keeps track of that. And then notice I list a variety of variants down there, 100 base T, Wi-Fi, 10 base T, gigabit Ethernet, and so forth. But they all kind of have the same kind of header information stored on the front of those packets. Now, one thing you'll notice I've been using datagram and packet as nearly interchangeable, but really there's a technical difference. And as I talk through the rest of this class, I might accidentally say packet when I mean datagram, but really they're both just groups of data. The distinction, the technical difference between them is we should probably use the word datagram when we're talking about TCPIP data blocks. So a datagram is a unit of data that deals with some block of data that we're adding headers onto the front of. A packet is more like a physical thing that's actually dropped onto the network. And so you might have a case where you have one IP packet that needs to be segmented or divided up into, so you have one IP datagram, we need to divide it up into these smaller physical packets using what's called segmentation. or fragmentation, I should call it. And the fragmented packet, as we go through there, those are packets, but it's multiple packets comprising or being formed from one larger datagram. All right, now, in most cases, a packet's going to simply contain a single datagram. So there's really very little difference between using those two terms, but in some cases, we might need to divide a datagram up into multiple packets. An example of that would be this networking type called X25, and it has a maximum packet size of 128 byte packets, and sometimes packets in TCPIP can be larger than that, like thousands of bytes or more. And so we need to kind of divide that up, put it back together, and that's where we use fragments to do that, and that would be individual packets. So most media, though, it's best to have one packet per datagram, and so that's what you'll see in most cases. All right, so let's start off with get into some of the details here. All right, so the details of a Tcp header. So this is just the TCP part of this. So notice that there's kind of two parts here. The header part, which is from here up, and then there's the data that we're adding the header to. Now this, notice it's variable length, so we could have a variety of different possible length data. There is a thing on most systems called the MTU, which is a maximum transmission unit. And if we have more data than will fit in one MTU, then we might need to divide this up into multiple datagrams. This also, notice this being variable length, it could be a length 0. We could send no data at all. That's okay. But what I want to do now is I want to dig into the header part of this, because that's what's being added to around the data that would be down here. And what I'm going to do here is I'm going to go through these kind of one thing at a time, or one group of things at a time. So let's start off with the top. So first off, the ports. The ports are essentially numbers. And you'll notice one thing about it. Let me go back for 1 second. Notice the way I have this laid out in ASCII art. Each of these hyphens or dashes is 1 bit. So you'll notice that this is a 16-bit port number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's 16 bits. And this is 16 bits. All right, so let's continue on, go through these. So the port number. Port numbers essentially are created to allow the TCP subsystem to keep track of different applications using the network subsystem for different communication conversations or streams. So in other words, when you're on a web browser, you might have Steam open, you might have some sort of chat application open, you might have, like, for example, Discord open somewhere. Well, all of those things need to talk using the network, but we don't want the conversations to get confused with one another. So the way that the TCP system keeps track of who is communicating from what application and getting responses back to that are for that application is it uses these port numbers. So the 16-bit source port is the port on your machine. The destination port is the number on the machine you're trying to connect to. So the idea of this is a way to get multiple applications to kind of share the network simultaneously without their communications getting crossed. So think of them like phone extensions, except that unlike phone or a mail stop, like a mail comes into the university, it has my name on it, it goes into my mailbox and not everybody else's mailbox or somebody else's mailbox. And so the idea there, think of these as like a mailbox number or a phone extension number. This is the one I'm calling from. This is the one on the other end that I'm talking to. And there are standard header or standard port numbers for particular types of applications. Okay, now there are 2 ports, one for the source end, one for the destination end. We talked about that. Notice they are 16-bit numbers. The source port is often called local, the local port, and the destination is often called the remote one. So this is the source port is the one on our machine, the local one. That's the phone extension and mailbox number that we're using to talk through. The destination port number is the one on the remote machine. That's the one that we're calling, the extension we're calling. Okay, moving down the header, we now have a sequence number and then an acknowledgement number. And notice those are this full 32-bit number here. So the sequence number and acknowledge number are 32-bit numbers. Now, those are used when we have to have a data stream or a large group of data that will not fit into one datagram, so we need to divide it into multiple datagrams. And the way that we know what order they go in is by the sequence number, and the way we know which ones were received and not lost is what the acknowledgement number is. So sequence number, it doesn't really number the datagrams sequentially using a counting sequence like 1, 2, 3, 4, but it numbers them based on the offset from the beginning of the data. So in other words, if there are 500, and notice I'm using the word octet here, I'm going to use that interchangeably with bytes, but on some systems, bytes are not 8 bits. So octet is kind of a preferred term when talking about that. An octet is just an 8-bit byte, essentially. So if there are 500 bytes of data in each datagram, the first one might be numbered 0, the next one 500, the next one 1,000, the next one 1,500, and so forth. So in other words, rather than saying this is packet or datagram 1, this is 2, this is 3, it numbers it by their offset. And the reason it does that is that makes it easier when you're filling in a buffer of data to put the data exactly where it goes, even if you're missing a previous part. Where if they were just numbered sequentially, you wouldn't know where they go into the data goes into that buffer until you get all of the previous ones. So this is can be useful. So think of them kind of like a page number or a character number in a book or issue numbers of a magazine, so you can tell when one is missing. So in other words, if I get 0 and the size of packet 0 was set to be 500, and then I get 1,000, I know that I missed the one at 500. Now, the acknowledgement numbers are used to verify the delivery of previous datagrams. So if I get a packet that has an acknowledgement number of one that I previously sent, then I will know that they got that one and everyone up to that one. So the idea is that when I receive an acknowledgement number that says acknowledge 1500, I know I got everything up to that. If I'm missing a packet and I don't get an acknowledgement number for a certain packet up to that number in a certain amount of time, I'll retransmit the one that was missing. And that's what it says at the bottom there. If the sender doesn't get an acknowledgement within a reasonable amount of time, it'll resend that data again. Okay, moving down the chart, we've got this TCP section with this 4-bit data offset. And what the 4-bit data offset is that's where the data starts, so after the header. So usually that's going to be essentially this 20 bytes worth of offset. And notice they are in 32-bit words. So if we go back to this thing here, notice that I have this in 30. This is each one of these rows is 32 bits. So the normal offset will be kind of 5 down is where that starts. So if we start at the top here and go 1, 2, 3, 4, 5, and notice some of these rows are taller just so I could put the text in there. But the idea is that this is 32 bits, one group of 32, 2, 3, 4, 5, and then we are on the actual data where the data starts. So that's usually what we're going to have in that offset, which is 20 bytes. And but it could be as much as 60. So if we max this out, there could be 60 bytes, which actually gives TCP the ability to have additional data added into after the header, the traditional header in the top of that. So we could call that optional header data. It gives us the ability to add that. Usually it's not used, but it could be if some certain application needed or wanted to send additional header information. Okay, now TCP details moving across. Notice there's that 6 bits of reserved data that I didn't really talk about. The 6 bits there don't really have any function. They're reserved for future use or just as ignore them, basically. But then after that, we have these. Each of these is 1 bit. 1, 2, 3, 4, 5, 6. We've got these 6 flag bits here. And what the flag bits mean is those are either set. They're binary flags, so they're either a 0 or a 1. And those have to do with TCP and its internal operation. The first one there, the most significant one, urgent pointer, that's whether it's valid or not. ACK is the acknowledgement number is valid or not. So when we receive an acknowledgement packet, the ACK flag will be 1, and then the acknowledgement number will be the packet offset, the data offset from the beginning of the data stream, that it's being acknowledged. PSH says the receiver should pass the data to the application as soon as possible. That's kind of a high priority packet flag. The reset thing says reset the connection. Synchronize says synchronize sequence numbers to initiate a connection. And then FIN says the sender is finished sending data. So that means we're now done. So in other words, as datagrams come across, where we have this large message divided up into these smaller datagrams, the last one in that group will have the final flag, the fin flag, set high, saying this is the last of the data I'm sending. And that tells the receiver, you don't have to worry about more coming in. This was the last of that. All right. Now, that 16-bit window size, the purpose of that is that controls how much data can be in transit at any one time. So in other words, it would be really slow if you think about, let's say, talking to a website on the or some system on the internet on the other side of the planet. If you send one packet and then wait for an acknowledgement, and then you send another packet and then you wait for an acknowledgement, that could be really slow to transmit data. So what TCP does instead is it says, I'm going to make and send a certain number of these packets at one time according to this window size. And then as I'm sending that, when the other machine is responding, it's going to reduce the window size as it starts running out of memory to store those things. So that way I can know to slow down my sending. So each end will indicate how much new data it's currently prepared to absorb, and it puts the number in that window size thing. And it's in a number of bytes in that window field. And if that ever gets to 0, where somebody sent me a packet and that's 0, I know that I need to stop because their window size is now 0. So this is kind of a way to control the flow of packets. So we're not overwhelming the machine on the receiving end, but we're also not going incredibly slow because we're waiting too long. So it gives us kind of this adaptive flow control where we're saying the window is going to start out large. As we send, it might shrink. As the receiver receives things and frees up memory, it'll grow. And so it gives us ability to adapt as we're receiving and sending data. All right. Last few parts here. We've got this TCP checksum. That's essentially computed by adding up all the bytes in the datagram. It's actually a little more complicated than that, but we're not going to go into the details of this. It's actually this thing called a pseudo header that gets used, but it's essentially we just add them all up, and the sum of that goes into that 16-bit checksum. That's used for error detection on the check or the header itself. So if it gets corrupted in some way, we have a checksum to be able to know that. Now on the other end, the TCP header on the other end gets read. It computes the checksum again. If they don't match, then something bad happened to the datagram. Something's gotten corrupted in the header somewhere or the checksum itself. So that datagram gets thrown away and not acknowledged. All right, the urgent pointer, that gives us a field that allows one end to tell the other end to skip ahead in its processing to a particular data byte offset. And that can be useful for handling asynchronous events, like you type some control character like Control C, and you have a big stream of data. You want to send that, still want to send the whole stream of data, but you want to say, hey, there's a Control C in this. This gives you this kind of urgent pointer way to jump ahead to some particular byte offset. And the urgent pointer only gets used, the value that's in this position only gets used if that URG flag is set. And remember in the flags, we saw that there. Urgent pointer is valid. Okay, so there's the summary of all of those parts. There's not a whole lot to it. We got the 2 ports. We got the sequence number, the acknowledgement number that are related to each other. We got the data offset that tells us how far ahead to jump to get to the actual data. We have got a set of flags. We got that window size, and we got a checksum, and then we have the urgent pointer. So notice that relatively small. We've got a 20-byte header here, essentially, for the TCP part of this. Now, one of the things you'll notice is missing. There's no addresses anywhere in there. There's no destination address. There's no source address. That's not the job of TCP. What the job of TCP is, if you remember, was taking a stream of data from one machine to another machine, dividing it up into sub-packets if necessary, these sequence numbers, and then making sure it reliably gets transmitted, which is what the point of the acknowledgement is and what these flags do, and getting them to the other end reliably. Now, to add addressing, IP. So notice that down here, this is where our TCP data and then our data would be. So in other words, on the front of the TCP packet or datagram, we're now adding this Ipv4 header. Now I'm going to talk about Ipv4 today. There's a newer variant called Ipv6, which has a different kind of format to it that allows longer addresses. But I'm going to talk about the classic Ipv4 today, and we'll maybe mention Ipv6 a little bit later in the semester. But if you look at this, it's 20 bytes as well, just like the TCP header was. But the 20 bytes are set up a little bit differently. So let's look at them. So we've got all these things here, but notice it does have addresses. It has a source address, has a destination address, and then that's on the front of the TCP header, which is followed by the data. All right, let's go through these one at a time. So version. The version's a 4-bit field. It's used to specify what version of IP the datagram is. If it's IPv4, there's a 4 in that position, a binary 4. If it's IPv6, the value has a value of 6. So notice that as they make new versions of IP, there's a way that, and notice that's the first thing in the packet. So if you load this packet up, you can immediately tell what version it is in those first 4 bits and use that to help you decide how to process the rest of that packet. Next after that is this internet header length. That is very similar to that offset we saw earlier. So in other words, this is a variable size. Again, it's usually 5, just like the header length was in TCP, but this tells us how far ahead to jump for the actual data. And again, the maximum here is 60, just like it was for TCP. In other words, this allows for optional things to be added into the IP header as well. That's the IHL field. Really, it says the same, let me go back for just a second, same thing as that 4-bit data offset in the TCP. Same concept, exactly. All right, after that's the type of service. And that had a lot of different uses over the years, but the idea is that type of service, the idea for that was to give priority to certain kinds of IP datagram traffic. So for example, if you have something that's a real-time service like voice over IP telephone, that needs to have a higher priority to route and get through the system than something slower like a file transfer. And so that type of service was used to that. And now it's been redefined to be this differentiated services code point, which is really kind of the same thing. And so things like VoIP will put a value in there that's different than a generic traffic. And it also provides a way for, as this IP thing, and remember, think of the IP header as the outside of an envelope with the addressing and stuff on it. It might have like priority mail versus first class versus whatever the other classes of mail are overnight. So that gives them gives the routers a way to prioritize certain types of traffic. All right. There's one thing we didn't talk about, that total length. The total length field that's on the end of there, that's the giving the total length of the entire datagram that follows. All right, identification. The identification field here, that's a 16-bit field that's used to identify the group of fragments of a single IP datagram. In other words, if we have to fragment an IP datagram into multiple things, then to make sure they all get grouped together to the same group, there's this identification field. All right, flags follow the identification field, and there are only 3 flags for IP, one of which is reserved, but it has to be 0. So the next 2 are the DF flag, or don't fragment, and then one that's the more fragments field. And essentially what those are, notice these all identification and flags and fragment offset, all this whole line here, this block of 32 bits, all deals with fragmenting packets. So more fragments and don't fragment. If the DF flag is set and fragmentation is required throughout the packet just gets dropped. So it's a way to say, hey, if this packet is too big to fit on your network, rather than trying to divide it up and send it and put it back together, just drop it. Just forget about it. Now, the more fragments field is useful because it basically says whether or not this packet is part of, or this datagram is part of another datagram, or is a fragmented part of another datagram, it needs to be put back together. So if the more fragments field is set, that means this is not the last packet or standalone packet. There's another one that's going to follow. If the next one is set, same thing. And if we ever get to one where more fragments is 0, that means that that's the last one we know to stop at that point. So all fragments except the last in a fragmented group of packets will have that more fragments field or flag set. So if we have a datagram that entirely fits in one datagram in one packet, it'll always be cleared until we need to fragment. It's almost like is this a part of a fragmented set, or is it the last of that set? All right, the fragment offset, it's used to measure the kind of length in units of 8-byte blocks. It specifies the offset of a particular fragment relative to the beginning of the original unfragmented IP datagram. So just like with these fragments here, they aren't sequential. They're not like 1, 2, 3, 4. They're not the counting numbers. They are in the offset as measured in kind of 8-byte blocks. So the first fragment would have an offset of 0. The next one would be, if we had an 8 in there, it would be 64 because it's 8 times 8 bytes, 64 bytes, and so forth. So it's similar to TCP's way of sending those offsets there, but this is for when we have one IP packet that needs to be, for whatever reason, put across the network where it needs to be divided up. It'll divide it up into multiple ones and then put back together once or after it's been fragmented. All right. The next line down in that header, the TTL field, time to live. The 8-bit time to live field is used to prevent, this was something that was actually pretty ingenious. The problem with a packet routed network is you might put packets into the network and you might think, well, they're kind of like a rat going through a maze. And so what if the rat makes a cycle, though, and ends up back where it started? And then we don't want it to get stuck in there forever, just constantly going in circles and circles and circles, never getting to its final destination. And that could happen unless we had some way to make sure that it has a lifespan. So their way of doing that was by adding this time to live field. And what happens is, if every time a router receives a datagram, it'll actually decrement the time to live field by 1. So it'll take it, reduce it by 1, and then send the packet on to its next generation. So notice that the IP packet headers are kind of being modified as the data is routed through the network. So in other words, it's not just like the letter as is. It says, oh, the count was 10, reduce it to 9, send it along its way. And if a router ever receives a datagram where the counter gets to be 0, we throw it in the trash. We say that one's been in here too long. It's hit its expiration date. We kill it. Now, one of the interesting things that happens with the TTL field is when the router discards the packet, it'll typically send a message back to the sender. And it uses the send address, and it says, sends this ICMP packet format message back to the sender saying, hey, I killed your packet. Its TTL expired. And interestingly, that can be used by programs like traceroute. If you've ever done a traceroute, what it does, it says, here's this message that I want to send, or what's the route that it takes to get from this place on the internet to this other place on the internet. And what it does is it starts off and sets the TTL field to 1. It sends it. The first router that gets it decrements it to 0 and sends a message back saying, hey, I'm at this location, I'm this server, I killed your packet. And then we set it to 2 and we do it again. It goes to the first one and that goes to the next one. And then that one kills it and sends it back. So traceroute, the way it's tracing those things through is using those kind of death notice messages that are coming back from each of the routers when the TTL gets to 0. So we start with 1, we go to 2, we go to 3, we go to 4, we go to 5, we go to 6, and so forth until we actually get to the end destination. And then we know the route that the packets would typically take to get to their end location. All right, the protocol field, that's an 8-bit field that specifies the protocol used in the data portion of IP datagrams. And really, there are a number of different protocol ways of kind of interpreting those. The ones that you're most likely to see are ICMP messages, Internet Control Message Protocol. I notice that's a little bit different than TCP, but it still uses IP as a service. But TCP is one of them, UDP is one of them. And TCP and UDP are very closely related. One guarantees delivery and segmentation. The other one does not. So UDP is like a unreliable mechanism, but can be much faster than TCP because it doesn't have to wait for acknowledgments to go on and so forth. And so we're going to be looking at these later on. But notice that this is just has a value and it says, hey, what is the data in this packet? What type of thing is it? So for us, any TCP connection would fall under this type 6 would be in there. The last thing we have is the IP header checksum. That's very similar to the checksum that's in the TCP header. Essentially, when a packet arrives, checksum gets calculated. One thing to note about this, though, is that the checksum in the IP header is not the same as the checksum when the thing was originally transmitted. And the reason, because the TTL field over here is being modified. Each router updates the checksum as it updates the TTL field. But in other words, if I get something where the values don't match, then something bad has happened to that packet. It's gotten corrupted. We throw it away. It gets discarded. And again, note that the routers have to calculate new checksums when sending packets along because the TTL field has been changed. So routers are not just kind of mail sorters. They're actually changing the contents of the envelope as the thing goes as well. All right, the last two sections, the addresses. The source address is who is sending the message. The destination address is who it's going to. We think of it like an envelope. This is who we're sending the letter to. And this is our return address, or this is our return address. This is who we're sending it to. And notice that those could be changed as well if we're using something that uses what's called NAT, which is Network Address Translation, like your router. You have a home router. You've got 6 different devices that are on the network. They all have a local address like 168 or 192.168.1.1 or 1.4 or 1.5 or whatever. Those are going to get translated by the router into a different address. So a router might change actually the source and destination address of things as we're sending it. All right, so notice that those addresses are 4 bytes. In other words, this is just a 32-bit number. And that's why you usually see that numbers and dots notation for websites. For example, 146.85.1.1. These are the bytes. So first byte is 146, second byte is 85, the next one is 1, next one is 1. But together, that makes a 32-bit number. And the reason why the numbers and dots notation is used is because it's a lot easier to remember that than it is to remember this giant 32-bit number. And also because the way that the net masks work for 146.85 will all be systems on one network. And it might even be 146.85.1 is all systems on one network and so forth. Okay, so there's the IP header. We went through all the fields of that one at a time. Again, only 20 bytes. So now we have the 20 bytes of the IP header followed by the 20 bytes of the TCP header. So we've got 40 bytes total, and then the data that we're wrapping inside of that. Now, the last thing, though, is this is still not something we can put on a physical network. So to put this on a physical network, we need kind of a data link layer, or Ethernet. So let's look at an Ethernet header. And the Ethernet header is actually much smaller. So doesn't have to worry about routing, doesn't have to worry about all that other stuff. It's really just a way to get the packet onto the network, the physical network. So it really has this 14 bytes worth of header data plus a simple 4-byte checksum. And that 4-byte checksum is at the end. And so we have the Ethernet destination address is essentially 32 bits here plus 16 more bits here. And then the Ethernet source, 16 bits plus 32. So in other words, we've got 48 bits for the destination, 48 bits for the source. And these addresses here are hardware addresses. And then we have a type code, which is a 16-bit type code. And that's it. That's all we have. So the only thing on an Ethernet packet, notice how simple it is. It just has the destination address, which is the first thing, the source address, which is the second thing, the next 48 bits, and then a type code. And that's it. And then after that, we've got the IP header, TCP header, the data, and then finally, at the end of all of this, we've got the Ethernet checksum at the very end. All right, so looking at that, 48-bit MAC address, both the sender and the destination, the type code, and then the checksum is at the end. And the checksum here does not just the checksum of the header. It's the entire packet that's being sent, the entire Ethernet packet. And you'll notice that it's put on the end of the packet because of that. So in other words, this checksum wraps the there has the Ethernet header as part of it, the IP header is part of it, the TCP part, and then the data is all included in this checksum. And that's on the end. And that's a CRC, cyclic redundancy check, is used to compute that. So it's a very reliable error detection method that's used for that. All right, let's talk a little bit about the addresses. So the Ethernet addresses, those 48-bit numbers, every Ethernet device or controller has one that's programmed from the factory and guaranteed to be unique. So the idea is that every manufacturer who makes some kind of Ethernet equipment has to register with the central authority, and then they are given a manufacturer ID number, and then in their manufacturer ID number, they use their own kind of sub range in that to define those. Now, so in other words, if you have a device like a laptop and it has an Ethernet port, there's some kind of hardware with a hardware MAC address associated with it. If you have a Wi-Fi adapter, it's got a unique identifying address on it as well. And when you talk to a network, you're using Ethernet, you're filling in that hardware address into that. And one of the things that there are, notice that's supposed to be two things. One is that, if you remember, Ethernet was kind of a broadcast medium, which means that as these packets that look like this get sent, your machine is only supposed to pay attention to ones where the first 48 bits match your MAC ID. It's supposed to ignore all the other ones. But some cards can be put into a mode where they'll accept all traffic, and so it allows you to sniff the network. You can put them into what's called Promiscuous Mode, and then they will get all of the packets that are intended not just for it, but for anyone. And network switches can cut down on that traffic going everywhere a lot, because it'll only pass through traffic for the MAC addresses that it detects on those segments. And so, but it is possible to cheat and get traffic that is intended for other Ethernet adapters, and then read that in and analyze it. One other thing to note is that while every card comes programmed from the factory, there are some Ethernet devices where you can spoof or fake that Ethernet packet address too, where you can change it. So you can pretend to be a different piece of hardware with a different address than you are. So one other thing to note, though, is that these are hardware addresses tied physically to the hardware. And you'll note that they aren't tied to the IP addresses. IP addresses are kind of software configured. These are burned into the hardware and associated with each machine. So in order to know who you're talking to with what IP address goes to what machine address, there's kind of a internal table that has to be managed that keeps track of who is at what IP address and what MAC address do I talk to talk to that person. Okay, now we've looked at all the different layers. So every one of those layers we've kind of taken a look at, and they all kind of stack up. And as a quick reminder here, you'll note that the cat's trying to get out. You can say hi. Hi. All right. Thanks. All right. Please don't attack me. Oh. Cat is not a fan of me talking to my laptop. All right. The application layer, remember that's using TCP, pushing data down to it. TCP divides it up, adds a header to each IP, then it passes it off to IP, which adds its own header with the addressing information, the logical addressing information, and then that passes that down, that IP datagram down to Ethernet that wraps it by adding that Ethernet header with hardware addressing information and the checksum at the end, and then that's what goes across the network. So a router will receive that packet, that Ethernet packet, and then it will say, it'll look inside at the IP and say, okay, I know where this needs to be routed to. So it'll wrap it in another Ethernet packet and pass it along. So notice, and also it's going to decrement that TTL field each time. So notice that the TCP field here in the application data doesn't really get touched or changed. But this IP layer has the TTL field changed. It might even change the addresses if we're using a network address translation router to access the internet. So this part might be changed. This part but think of it as an envelope. We take our data, we stick it in a TCP envelope, we stick that in an IP envelope, we stick that in an Ethernet envelope. The Ethernet one is going to, for every transmission from one site to the next on the internet, is going to get unwrapped, rewrapped, unwrapped, rewrapped, unwrapped, rewrapped in a new envelope every time. The IP one is going to have its envelope just modified slightly, change the TTL, decrement it by 1, rewrite it, update the checksum, pass it on. Or maybe in the case of network address translation, it'll swap out the address that we put in there, our local address, 192.168. something. That'll get translated to the address of the main system that goes out on the internet. When traffic comes back for that one, it'll translate it back again. So notice, though, that it's the layered approach of this is wrapping the application data all the way on the inside of the envelope, TCP around that, IP around that, Ethernet around that, and that allows us to strip off the network-specific parts while preserving the stuff inside to be sent to the application. Okay, so here's a kind of a picture representation of that. Here's the user data that comes from the application. The application might add its own header onto that data to keep track of, like if it's a game packet, it might add its own meta information on the front of that to say timestamps or whatever else. It could add its own header. But then that has the TCP header added onto that. And then that gets passed down to IP, which adds the IP header on the front of that. And that gets passed to Ethernet, that adds the Ethernet or frame header on the front of that. And you notice the total amount of data that we've added is 14 bytes for Ethernet, 20 for IP, 20 for TCP, and then 4 at the end for the Ethernet checksum, this 32-bit CRC at the end. And that's going to be a CRC of this entire thing up to there with however much data we have in there. And then that's what goes on for the internet. So the part that's getting stripped off every time is this Ethernet frame header part here. And that it's going to get stripped off, reformed, stripped off, reformed. But the IP part and TCP part are going to pass through. And when it gets to the receiving end, it's going to do the opposite of this. The Ethernet thing is going to receive this, pass this part up to IP. It's going to then strip off the IP part, pass that up to TCP. And TCP is going to then use the sequencing information and to then send acknowledgement packets back or put them together in the right sequence and so forth. But the only time any of this up here will get it is if it was received correctly and the CRC passed. Otherwise, that gets discarded. Okay, a couple quick questions here that I'm going to leave for you to ponder. First off is, how many different possible IPv4 addresses are there? And how many possible MAC addresses? I'm going through these in a slightly different order, so let's start with these ones. So remember, IPv4 was that numbers and dots notation, 146.85.1.1 or 206.23.94.1, whatever. But this IPv4 address, notice this is like 4 bytes. So with 4 bytes, how many total addresses can we get? And that's actually the answer to that is why we have IPv6, is we were starting to run out of IPv4 addresses in the address space. So there needed to be a way to add more. They made a new version of IP, which has larger sized addresses associated with it. How many different MAC addresses are there? Remember, that was a 48-bit Ethernet hardware address. Again, 48 bits as opposed to 32. Gives us the ability to have quite a few more possible addresses here. Now, one of the things, what stops a machine from using an IP address of another machine if that's software configured? Well, the answer to that is something worth thinking about. So, for example, could I just change the IP address of my laptop to be the same IP address as Google and start getting traffic that was intended for Google? So think about that. What stops a machine from using a MAC address of another machine? So let's say I'm on this local network and I notice that there's a security camera and it's an Ethernet-based security camera. So I look at the MAC address printed on the side of that. What's to stop me from making my laptop have that same MAC address and then receiving packets that were intended for that security camera security system? So think about that one. And then how does the machine know the MAC address of the destination machine? So in other words, when it goes to send a packet, how does it get the MAC address? So I want you to think about these. We'll talk about these at a later point. Might be good to have a quiz about some of these things here, but I want you to think about those, investigate them, and come up with an answer that kind of makes sense for yourself. See if you can come up with the right answer. All right, so that's all we're going to do today. Next class, we're going to actually start writing TCPIP programs. So rather than just looking at the overview of this and those headers, we're going to look at how through code do we do this. And one of the nice things is, remember that I said that TCPIP kind of presented a library of routines that we could call, think of it like a module, like a code module that we can use our code library. And so really they're just some function calls we have to use. So in other words, we're not going to have to worry a whole lot about behind the scenes how TCPIP handles all the kind of segmenting things and putting them back together. It's good to look at the header and have some understanding of it. We're not going to worry about all of the low-level details associated with that. But what we are going to do is we're going to write code that talks from one machine to another machine over the internet. And we're going to learn how to use kind of that library to do that. And that library we're going to look at is called the sockets library. And if you think of what a socket is, it's like a connection from one end to one location to another location. But behind the scenes, it's going to be using TCP, which is going to be using IP, which is going to be using Ethernet and going through these routers. But the cool thing about the way TCPIP was designed in this layered approach from our application, it can be as simple as saying, open this connection, send data over the connection, receive data over the connection, close the connection. But that's going to be different if we're on the sending or the kind of client side or the server side. So there's kind of two ways we're going to have to look at the coding of that. One for making servers, one for making clients, and we're going to do that next time. So until then, stay safe. If you have any questions, ask them in the comments of the video or on email or text message or on the class site. So feel free to ask any question that you have about any of this. But it's actually a really cool technology that we're going to be programming next time. It's really how everything on the internet works. So we're going to be focusing on that next class. All right, until then, stay safe.